Welcome also from my side. My name is Heiko Herden, and I'm with the VDMA for 5 years now, and I'm in the OPC UA team in the section Machine Information Interoperability, and my specific role is the coordination of all the working groups and the harmonization of the OPC UA specifications. And for today's presentation, I brought the following agenda. We will start with an introduction to OPC UA for machinery, which is the main topic of today. And then we will have a technical deep dive into the different documents. So OPC 40,000 Part 1, Part 2, Part 3, Part 101, and the OPC 34,100 energy consumption management, as this is also relevant for OPC UA for machinery. And then we will close the whole presentation with an outlook. So let's start with the introduction. First of all, we need to discuss why we need OPC UA for machinery. And this is because we want to achieve a manufacturer-neutral interoperability in the industrial environment. And when I talk about interoperability, you might already know that from your personal life, from your consumer life. If you go to some hardware store and buy a computer mouse or a printer, you can just connect it to your computer, and usually it should work. So this is called plug and work. And also, if you buy some cell phone which supports the Bluetooth standard, and you buy a car which supports the Bluetooth standard, then you can connect it and exchange information and work with this. And as we know it from this consumer life, we also want to achieve the same in the industrial context, but there it's a bit more difficult as the industrial context is very complex and very individual. So if we take a look now at this graph, we will see that interoperability is the goal we want to achieve. And we are coming from Industry 3.0, which means proprietary communication, now into the field of Industry 4.0. And the first step to achieve interoperability is to get all the different components, machines, and systems into one network so that they can exchange data. And for this, we use the technology OPC UA. OPC UA stands for Open Platform Communications Unified Architecture, and it brings all the advantages that the mechanical engineering industry needs for such a technology to get everything in one network. So it is open source, it has security built in by design, it supports various protocols, it has the possibility to have a semantic machine description within, and it's highly scalable. So I can use it on a small edge device, but also on a full embedded Windows computer. And the nice thing about OPC UA is with all these different protocols, I can also do client-server communication. I can do publisher-subscribe communication. I can even do MQTT over OPC UA. So it's really a very good technology to build on for our interoperability approach. But OPC UA only solves how the data gets from A to B, but it doesn't really solve how the data looks like. And that's now where we need to address with information models. So we define domain-specific but harmonized information models. And this we do in so-called OPC UA companion specifications. If we now take a look at the structure of the VDMA, we will see that we have several organizational units. And now here on this slide, I brought an overview of all these units. And I used a blue color for the ones that have already published an OPC UA companion specification. And I used the orange color for those that are still working on it and don't have any published specification yet. And as you can see, it's really a lot of different domains. I won't go through all the domains, but it's more than 25 sectors. And in some, we have over 100 companion specifications that have already been released. And as you can see, there's a lot more coming up. And also the fields that are marked in blue don't necessarily mean that they are done. Maybe they are working on a second part or on another machine type within that domain. So there's really a lot of work going on in this field of the definition of OPC UA companion specifications. And what we realized when we defined all these interface standards is that some information is the same in all these different domains. There are information that are so generic that we don't need to solve them in a robotics spec or a machine tool spec or in a woodworking spec, but that they really can be addressed in a more general approach in a cross-domain harmonized information model. And so some years ago, we started with this activity and we called it OPC UA for machinery. And in OPC UA for machinery, we address exactly these topics that should be solved for the whole mechanical engineering industry. So topics like machine identification, component identification, machinery state, process values, result transfer, counters, or job management. These are the already published building blocks. But of course, we are not done yet. We are still working on further building blocks at the moment on the basic server structure and on a building block for energy management. And with this approach, we always bring out one building block by one building block so that the already defined building blocks can be used as fast as possible. The advantage is pretty clear, I think. Let's take a look at a machine park where I have a lot of different machines from different domains, and I want to access the data of these machines. And first of all, I can connect via OPC UA. Then I will see what kind of machine or system it is with the machine identification, for example. And then I will get the information in the same way from all these machines. So for example, the status of the systems or machines or the energy consumption. I get it all in the same way. And therefore, I can also compare it and do things with it. I can throw it into a AI. I can do KPI figures with it. So there's really a lot of interesting use cases on how to use information coming out of the shop floor. So, but let's focus on what is OPC UA for machinery now in detail. So OPC UA for machinery is basically also a companion specification, but for the whole mechanical engineering industry. And in OPC UA for machinery, we define harmonized basic building blocks for the broad use. I already showed all these topics. So each topic is one building block because each building block stands for a specific use case. And if you now ask a question, how would I use OPC UA for machinery? There are basically two ways. You can either have it referenced from another companion specification. So for example, you have the machine tool specification and it already uses OPC UA for machinery, or you can use it as standalone model. And here on this slide, you can see that OPC UA for machinery really forms the basis for all these different domain-specific companion specifications. So if I want to look at an interface, for example, from a laser machine, then I will see that I have a combination used. I use the machinery specification for the, let's say the base information, the generic information. On top, I will use the machine tool specification because a laser cutting machine, for example, is just a more specific kind of machine tool. And of course, I also need the laser specification for the very specific information like a laser power. If I take another look at an interface, for example, of a woodworking machine, I would have the combination of OPC UA for machinery and OPC UA for woodworking. And as user, you just need to have the woodworking specification because the woodworking specification already uses OPC UA for machinery within. Now let's take a look at the document structure. I mentioned already that OPC UA for machinery has these different building blocks defined, and you will find most of the building blocks in the document 40,001 part 1 basic building blocks. But other building blocks you will find in part 2 or part 3, so for process values and job management, or also in part 101. So what we did is we said we need these different specifications so you don't have to use everything every time. and we use the numbers starting from 101 for things or for topics that we thought are a little bit less generic, but still needed from several domains. And so what we are going to do now is to take a look at those single building blocks in these different documents so that you get an idea of what we have defined in OPC UA for machinery. So let's get started with OPC UA for machinery machine identification. The question at hand here is if I want to connect several machines, especially from different domains, I want to see to which machine I am connected and who built it and where it is standing and things like that. And now with OPC UA for machinery, this information is provided in the same way. How does it work? We defined a so-called machine identification type, which comes with a lot of different properties. These properties are mostly inherited from the OPC UA base specification part 100 for devices to also gain an even higher interoperability so that we not only have an harmonization within the mechanical engineering industry, but also to other industries. And as you can see now, we have all these properties. There's this long row of properties on the left side and these 3 properties on the right side. And the properties on the left are usually properties that are filled in by the vendor of the machine who sold the machine. He can already fill these in. It's things like manufacturer, model, product code, hardware revision, serial number, year of construction, initial operation date, and stuff like that. And on the right side, we see properties that can be filled in by the customer of the machine. So the person who bought the machine or the company who bought the machine can give the machine its own asset ID, its own component name, or the own location, which could be something like hall 4, line 2, position 3 or something. And in OPC UA, in our information models, most of the properties come as optional properties. In this case, we have 3 properties that are mandatory, and we need those 3 properties to be mandatory to achieve a unique identification. That's a little bit different if we now take a look at the component identification. It's very similar to machine identification, but in this case, we don't have the location property as the component is always part of the machine, which already has a location. And we have one additional parameter, the device revision. In this case, we only have 2 mandatory parameters, which is the manufacturer and the serial number, because here we didn't need a unique identification. How does it work together? If we now take a look at the OPC UA information model, and if you're not familiar with this, it's very similar to how you would browse through a Windows computer. So we have an entry point, like a folder, which is called objects. And in there, we will find a folder for machines. And within that, we will find all the machines that use the machine identification. And within each machine, on the other hand, we will find a folder for components. And this folder lists all the components which are specific to that machine. And there's also the special case that, for example, a machine can be a component of another machine. But so just by using the machine identification and the component identification, I get a very well-structured information model. Now let's go on to the next building block. This was identification. And now we are going to take a look at the machinery state. So again, there's the question, why do we need this? And again, it's especially good if you are producing with a lot of different machines, because as I can tell you, I was part of that group in different domains and different manufacturers solved the machinery state different before we had the specification. If I asked 5 different people how they would call that the machine is currently producing, one would say it's called working, the next would say it's called running, it's called executing, it's called production, or maybe something like dry run. So there were a lot of different names out there. And of course, you can imagine how tricky it is to work with all these different names because you need to do a mapping each time. You need to see, does it mean the same? And with our machinery working group, we now solved this issue by defining the machinery item state. And it took us quite a while to define this machinery item state because, of course, everybody is used to their own names and definitions. But in the end, we came up with a solution that really worked for everybody. And it's a simple solution, but maybe that's exactly the reason why it works for everybody. So we defined 4 different states. There's the state of not available, which means the unit is not available and does not perform any activity. Examples are that it is switched off or in some energy saving mode. There is the state of out of service, which means the unit is now available, but it's not functional. So we are in some sort of error or the machine is blocked by an open door or something. Then we have the state not executing, which means the unit is available. And this time it's also functional, but it's still not performing any activity. It might start or it might wait for something like that a job is sent there or that some action takes place from inside or outside. And then there is, of course, the executing state, which now means that the unit is available, the unit is functional, and it's actively performing an activity. And if we now go back to the picture of the person wondering what all these states mean, this person now has clarity. He gets the states in the same way from all these different machines. He can compare them, he can use them to do whatever calculations. So if we just look at this machine view, it's already a great help. And with machine view, I mean like looking on the machines. But we can also take a look at the component view. What happens if I look into the components? So in this example, I have a machine, which is a beverage filling line. And the whole machine is now in the out of service state, indicated by that red light that we can see next to the machine. And now, usually I would wonder, why is it out of service? What's the issue here? How can I solve the issue? And what I could do now is I can browse into the different components of this machine, into the conveyor, the injection, and the gripper, and see how the machinery item state is for these components. And then I will see that the conveyor is not executing, the injections are not executing, so both are functional, but the gripper is also out of service. The gripper has the issue here. And this might be because it's jammed, for example, but I know what to address to solve the issue overall. So this is just another example of how helpful these machinery item states can be. On top of that, we also defined the machinery operation mode. Again, we have 4 different states here. We have the state none, so we don't have any operation mode. We have the state of maintenance, the state of setup, and the state of processing. And I can put these different modes depending on what I want to do. If I want to produce something, then it's processing, of course. But I might do setup runs or cleaning runs or whatever, and then I would put the different other operation modes. And now with the combination of the machinery operation mode and the machinery item state, I can do things like KPI calculations for the machine availability. So I brought an example here where we have a machine that should produce over a time of 8 hours. So the planned busy time is 8 hours. But if I now take a look at the different states over the day, I will see that I'm out of service for 2 hours. I'm not executing for 1 hour, and I'm executing for 5 hours. So from the 8 hours of planned busy time, I only have an actual production time of 5 hours. And if I divide one by the other, I will see, oh, it's only 62.5% of availability. And this is just another example to show you how these simple states already can make a big difference in how you can use the data. How did we solve this? Our modeling approach was to define a so-called state machine where we wanted to have all transitions allowed. So you can go from each state into whatever other state. And the good thing about this concept is that these state machines can be extended by substates. That means that other companion specifications can use the states and define substates to their own needs. Because, of course, at some level, the domains are not so easy to get under one head. At some point, they need to define something more specific. And that was done, for example, with the extrusion companion specification. So they defined substates for the topic of executing, and they said when it's in executing, it can either be ready to run, controlled run, or manual run. And in my opinion, that's a super interesting example, because the ready to run in almost every other domain would have been part of not executing. But for the extrusion, the machine needs to be temporized all the time. It needs to heat up to be in that ready to run state. And for that reason, it's in the executing state. So that's how we solved it. And I hope that you got a good idea now of the machinery state, because now I'm going to move on to what is behind the topic of counters. And it's a pretty simple topic, I would say. We defined a so-called machinery operation counter type, which is also inherited from the devices specification. And there we have three different properties. We have the power on duration, which defines the duration that the machinery item has been powered. We have the operation duration, which defines the duration that the machinery item has been powered and was performing an activity. And we have the operation cycle counter, which defines a counter that the component switched from not performing an activity to performing an activity. A good example where to use this would be evolve, for example. Furthermore, we defined the so-called lifetime counter with different properties like engineering unit, start value, limit value, indication, and warning level. And to bring it a bit clearer to you, I brought this example, or actually it's two examples. It's one example where I have a software license that is valid for 1 year, so 365 days. And on the other hand, I have a tool which can be used to produce 1,000 parts. And what I will see here in these examples, the software certificate validity lifetime counter counts down. So we are at the moment at a value of 200. So we have 200 days left, and we will get a warning at 10 days and an indication at 0 days. And on the other hand, the parts produced counter counts up. So there we have the current number of 553. And here we count number of parts, and we will get a limit indication at 950 and will reach the final limit at 1,000 parts. So that's that about the counters. And let's go on to the process values. Like I mentioned, the process values now is the part 2 of OPC UA for machinery. And this one is meant for getting information about values that are usually measured by sensors, for example, a temperature, in the same way. So if I would ask my different machines with their different sensors, at the moment I might get the right information, but I might get it in a different format. For example, here temperature is at 53 degrees Fahrenheit or 301 degrees Celsius is the temperature at a nozzle, or something says my blade is at 450 K. And now with the specification, I will get the temperature in the same format. Of course, I can still use different engineering units because I use the mechanism from engineering units, and I also recognize which unit it is. And so what we did here is we solved all the requirements in this machinery part 2, which were we wanted to address an actual value, a set point value, an engineering unit, an instrument range, deviation limits and general limits. We wanted to have a status, whether it's in range or out of range. We wanted to have alarms, a 0-point adjustment, even a substitution value if we lose the connection, that we still have some substitution set point value. And we also wanted to include a device identification and health. And some of the properties here are derived from the PA-DIM specification. So once again, we're not only doing harmonization within the field of mechanical engineering, but we are really doing the harmonization with other domains and, of course, with the OPC Foundation in general. How does it look in the information model? So we defined a process value type, which has an analog signal. And within the analog signal, you will find all the properties that I just mentioned with those different limits, for example, an EU range, an instrument range. And on top of that, we also have the set point. And once again, also the set point has these kind of limits or deviations, which are like with addressing the set point. So if I change the set point, the deviation will change as well, as you can see in that graph on the right side. And on top, of course, like I mentioned, we have things like a method for 0-point adjustment. We have a deviation alarm, a limit alarm, status, and a chance to do an alarm suppression. So that's that about process values. And now I'm getting to maybe the most complex, but also super relevant topic of job management. First of all, we are talking about machine jobs and not some orders that come into some online buying platform or something. We are really talking about machine jobs. And here the principle is that I have a machine and I have a higher level system. And the higher level system will send a job order to the machine. In this example, we have some log, which is processed into a table plate, 4 table legs, and a bag of wooden chips. And at some point, the machine will schedule and start the job. And there we also get a status change notification. And from then on, the machine will execute the job. And we can, of course, also request status information within that process of the job being executed. But in the end, we will get a job result. And that job result will tell us about all the specific information that occurred during the processing of the job. Then we can store the result. And in the end, when we are completely done with the job, then we can send the information that we can clear the result on the machine, because usually a machine only has a limited amount of space to process those things. In general, the job management specification followed the approach to use the OPC UA for ISO 95 Part 4 job control specification. So once again, you can see we are doing harmonization not only in the field of machinery, but also with all the other domains. And on top, we defined the information on what is to be exchanged. So that we did in the part 3 of OPC UA for machinery. And there we are sending information like plant information, what is the plant start time, what is the job name, what is the required material. We can get the status, but we also get actual results. So what was the actual produced material? What was the actual start time? What bill of material did I have? What was the performance info of my job, for example? And what I would like to show now next is that middle part here with the status, because also for job management, we defined a job state machine. And this job state machine is applicable for each job on the machine. So for example, if I send 3 jobs to a machine, you will find that each of these jobs has a state out of the state machine. And if I send a job, the job will be in the prepared state at the beginning, which is either allowed to start or not allowed to start. And then we have the running state, which is for working on a job. We can pause the job and get into an interrupted state, but from there we can also resume the job or abort it or stop it or whatever. We have the aborted state. From there we can't resume the job. At that point, the job is over and usually not successfully over. And of course, we also have the ended state where we finished the job. And as we followed the ISO 95 approach, we also modeled the other states from ISO 95, but as optional substates. So as you can see here, we have the states of waiting, ready, and loaded within the prepared. We have a differentiation between held and suspended for the interrupted state, so whether it's interrupted from the inside or the outside. And the ended state is also differentiated between completed, which means the job is really done, and ended, which also means that the job is really done, but also that the processing of the data is done and that you can delete the job. And the waiting ready and loaded means whether, for example, the preconditions are met already. So let's say I have a job where I want to paint something in, let's say, green, and I have two other jobs that want to paint something in blue. And if I put in the blue color, then the blue color jobs will jump to ready because that's the precondition that had to be met. But the green job would be going back or still staying at the waiting state. And loaded would mean that I have loaded the necessary recipe or configuration to do the job. How is that solved now in the information model apart from the state machine? So we are having the job management type now in OPC UA for machinery, which consists mainly of two things. The job order control, which is referencing the ISA 95 job order receiver object type, and the job order results. But let's look at this job order control first. So this we use to receive and control job orders. There we will find an array of job orders managed by the object. So in the job order list, I will see all the job orders on the machine. And we have all these optional control methods that we have just seen as arrows in the state machine. I can also have recipes or configurations within that work master here in that type. On the other hand, we have this job order results, which provides all the results of the job orders. And here we have a method to poll these results. We get an array of job order results, and we can also have an event for the job order results. This also needs to be integrated into OPC UA for machinery, of course. And for that, we use, as with the other building blocks, the machinery building blocks folder. So this is just an add-in called job management for the machinery building blocks folder. And within that add-in, I have the job order control and job order results. And in the machinery building blocks folder, I will see all the other different building blocks from OPC UA for machinery. And as I mentioned already, in OPC UA for machinery, we defined a lot of information that is planning information that needs to go into the machine together with the job. And here you can see a list of it. The green marked things are properties that not only need to go in, but also need to go out. So the job name, the order number, customer order ID, job execution mode. But on top of that, we have information like runs planned production time, planned setup time, and so on. While on the other hand, we have this out information. Like I said, the green properties are the same as that had to go in already, but here we have information like what runs are completed already, what runs are started, what's the actual production time, the actual setup time, or what is the estimated remaining time. So this is really not the planned information, but the actual information. And on top of that, we defined additional data types, like for the job execution mode, or whether the job result is that it was successful or not, or it's okay or not okay. And all these properties are optional in OPC UA for machinery, but of course they can be made mandatory by other companion specifications that use OPC UA for machinery. We also can get a huge chunk of information, I would like to say, out of this job management model for the results. So for example, to see what is the actual produced material, where we can add a lot of parameters. So we just defined a structure, but the parameters can be added. In this case, we have this table plate or this shelf floor with parameters for how big it is or how thick it is, for example. Or the same also for these table legs or the bag of wooden chips that I mentioned earlier. Or I can also use it as a bill of materials so that I build something, for example, this shelf floor, and I will see from which parts this was built. In this example, it was built from a specific tree trunk. And this can be also very helpful, of course, if I want to have a certain traceability of where my products come from, especially if I want to do some error following or some quality management of parts. Then let's go on to the topic of result transfer. As I already mentioned, this topic is a bit more specific. Not every domain will use result transfer. It's used by the machine vision, for example, by textile testing devices, by the IJT group, so the joining group, which also has these kind of complex measurement results. And here the requirements were that clients shall be notified if new results are available, that clients shall be able to access individual results, and clients shall be able to filter for specific results. And so we solved that by defining different mechanisms how to access the results. So there's the result ready event. We have a results folder where you can browse the different results and return the browse. We have two methods. One is the get latest result and one is the get result ID list filtered. But I don't want to go into detail too much for this topic. As I said, it's a bit more specific. Another topic that is not so specific is the topic of energy management. And in this case, we didn't solve it as an OPC 40001 because we wanted to be more specific here, but we not so specific here. We wanted to be more harmonized to bring in more stakeholders. And so we started a working group together with OPC Foundation, but also with the ODVA and with the PNO. And we called that working group Power Consumption Management and have now released a specification which is called Energy Consumption Management, as the mentioned part number here, which considers two different things. For one side, the power metering and monitoring, and on the other side, the power standby management. These things can be used to solve different use cases. So the power metering is about energy metering, do optimization, evaluate energy cuts, maybe also do predictive maintenance, while the power standby management really is about saving energy in intended pauses, but also in unplanned pauses. And so for the power standby management, we have a state machine defined how to get a machine into a standby mode or even to get into some switched off mode, which can be woken up on LAN. So like that you send some magic package to the machine and it starts up again. But I don't want to go into detail too much about the power standby side. I want to show you the power metering and monitoring now, for which we defined the energy measurement type, which represents a point in the system to measure potentially several energy data. Within that, we have the application tag, which uniquely identifies the functionality set by end user or system integrator. And within the energy measurement type, we have the measurement value for each measurement. So we can have several of these measurement values within one measuring point. And here we will see a lot of different information defined or different properties defined in the energy measurement value type, like the accuracy class, accuracy domain, accuracy range, measurement ID, and so on, as you can see here on the right side. We also have this reset function, and I think it gets a little bit clearer if I show an example also out of the companion specification. So here we have some sample object which has a power meter defined by the energy measurement type and an air extraction defined by the energy measurement type. And the power meter now provides three different measurement values: the AC active power, the active energy consumed odometer, and the active energy generated odometer. While on the other hand, the air extraction defines four different measurements, the pressure, the volume flow rate, the volume, and the temperature. And this is really a standard sensor that can measure all these things, for example. And you get a clear idea on what kind of measurement information it is by the usage of the measurement ID. So together with the companion specification, we not only define the specification itself, but we also attached a table, an Excel file basically, with at the moment 252 standardized measurements with predefined names, description, units, a predefined measurement period, and a predefined data type. So whatever kind of energy you are measuring, you can pick it out of this table and describe it via the companion specification. So this is also a very generic approach on how to fulfill the needs for energy consumption management. But in the end, we also want to create a new building block in OPC UA for machinery that provides a type definition or instance declaration for typical industry relevant measurement points, so that you don't have to look through those 250 values, but that you just get a standard set of measurement values. And so this will work as a collaboration between OPC UA for machinery and the research project Factory X, or industry project Factory X, and we will base it on this 34,100 specification, and it will become a new OPC UA for machinery building block in the end. So this was now a very extensive overview of all the different definitions we have made in OPC UA for machinery. Let me give you one last idea on how this works together with, for example, other technologies like the AAS, with the example of energy data. So I have a machine which measures energy. It has a power meter, and this shop floor information is now provided over OPC UA, and of course also hopefully over OPC UA companion specifications, for example, the energy consumption specification. But this energy data can then be used in different applications. So we could have asset administration shell submodel for digital nameplate or carbon footprint or energy monitoring. We could have a peak load management system. We could have a KPI monitoring. We could send it into the cloud. We could use it for some artificial intelligence. So there could be really a lot of different data things. But for us, the important part is that we only have one interface down to the shop floor to the machine. And we don't want to need 20 different interfaces. So on the OT level to the IT level, we want to use these OPC UA companion specifications, especially machinery. And on the IT level, you can have a lot of different data things, which can also use, of course, external data sources from the engineering, for example, but also for the carbon footprint, you might need some information from the energy provider, which kind of energy mix you are currently using. And so as a last outlook for today, we could say that OPC UA for machinery is really enabling a lot of upcoming trends. I already mentioned AI, but also data spaces, EU Data Act, digital product passport, product carbon footprint, digital twin, manufacturing X, overall efficiency calculations. It all needs information from the OT level, from the machine. And with OPC UA for machinery, we have an easy and good way to receive this data in a uniform way and use it in a standardized way. So that's it from my presentation for now. Thank you very much for listening. I know it was a lot of information, but I'm also looking forward to solving some questions that might have come up during my presentation.